Hello friends, welcome back. So, in the last class we have seen that we did turbulent non-premix flames. So, in this class we will start with turbulent premix flames and go into several aspects of it. In this class on turbulent premix flames we will mainly go into a lot of the physical aspects of it, like the structure of turbulent premix flames, which we will explain in terms of things called regime diagrams, which we did on a little bit for non-premix flames also. And then we will introduce some modeling approaches, in the sense which we will call this G equation approach, as well as the Bray-Mosley models. And subsequently we will introduce a very important quantity for turbulent flames, premix flames, called the turbulent flame speeds. So, as such, you have seen that for laminar premix flames, the most important quantity that determines the most important property of a laminar premix flame is a laminar flame speed. Similarly, the most important property for a turbulent premix flame is the turbulent flame speed. So, we will go into that and towards the end of this class. Okay. So, first we will go with basically these things called we will go with this regime diagrams. Okay. And then we will go with this G equation model, Bray-Mosley model, and turbulent flame speeds. And the majority of this material is mainly taken from the turbulent combustion book by Norbert Peters, and little bit from the turbulent flows by Pope also. So, where do we find turbulent premix flames in engineering devices? Turbulent premix flames is found in SI engines, spark ignition engines, and car engines, which are used in car engines, and in gas turbine engines, of course, and mainly in stationary power plants and industrial gas burners you find turbulent premix flames. Now, gas turbine engines, as we have discussed in last class, that mainly because gas turbine engines use liquid fuels, the flames that are formed are mainly non-premix flames, but still, as you have seen, that in non-premix flames you really cannot control the temperature as such, or the temperature of the flame, though you can control the exhaust gas temperature by dilution with the excess air, but the temperature of the flame really cannot be controlled for in non-premix flames, and that leads to formation of this pollutants, and stoichiometric combustion or near stoichiometric combustion, rich combustion leads to formation of this soot. So, you really cannot avoid pollutant formation in non-premix flames. Now, whereas we have seen that for the premix flame, of course, the premix flame temperature is totally controlled by the stoichiometry. That is, if you have a fuel lean mixture, of course, the temperature is less. If you have a stoichiometric mixture, the temperature is high. So, that is why you have a better control on the flame temperature if you have a premix flame. Okay. So, that is why it is we in the gas turbine engines, even for the aircraft engines, with the stringent emission norms that are coming, the aircraft engine industry is moving more and more towards premix flames, and as such you have seen in the last class also that this very modern engine, this GE and X engines, which they use for powering the Boeing 787 aircraft, and the TAPS combustors that they use, 2 annular premix solar combustor, and that is essentially a lean premix pre-vaporized combustor. Okay. So, it is a large fraction of the flame that is formed in this TAPS combustors, or this GE and X engine combustors. They are essentially premix flames. So, as you have seen, the industry, even the aircraft industry is moving towards premix flames, and the reason is simply the following, that you can have much less pollutant formation in this kinds of combustors. So, that is why the gas turbine industry is shifting more towards lean premix flames. Okay. And then of course, it has, you have to have the additional process of premixing. So, we are moving towards that, and that is why it is important to understand how turbulent premix flames behave. So, here on the right hand side you see this image or this video of turbulence, like a turbulence impacting on a initially flat premix flame. Okay. So, this blue surface initially is a flat, it is essentially a laminar premix flame, and then turbulence comes and impinges on that. Okay. So, this surface is actually a representative surface of the premix flame. So, it is essentially an isosurface of temperature of about 500 Kelvin, which is selected from the premix flame. So, you see that premix flame has this kind of a structure, right. The temperature increases like this is unburned, this is burnt, okay, and this is the burn gas temperature, this is unburned gas temperature. So, you can select actually one particular temperature inside that, which is 500 Kelvin, and you can when you basically look at it in 3D, it is essentially a flat surface like this. If it was a laminar premix flame, right, planar laminar premix flame. Now, then this turbulence comes on it and impinges and it creates this sort of different things. But what this does, this actually you see the different vortex, this is actually a beautiful visualization of the turbulence also. This is essentially you get this vorticity structures, this fine scale vorticity structures that are forming on the premix flame. So, you see that in this premix flame what it happens when as soon as it impinges on this surface, it essentially folds and wrinkles the surface at a multitude of length and time scales. Okay, and this length and time scales are controlled by both turbulence as well as the intrinsic flame properties. Okay, and then after it folds and wrinkles the premix flame at a multitude of length and time scales, you see that this surface essentially annihilates in this trailing regions of the flame. So, the flame, this turbulence essentially stretches, folds and wrinkles the surface at different length and time scales, and then this surface is actually destroyed. Okay, this isosurface of temperature is actually destroyed. So, then that means there is a continuous generation of surface also. So, a premix flame structure that you have, a turbulent premix flame, is this complex this convoluted wrinkled structure that you see is actually characterized by continuous generation and annihilation of the turbulent of the surface of the flame surface by turbulence. So, this is how turbulence actually interacts with the premix flame, and this interaction between turbulence and combustion and the flame is what gives the resultant structure. So, the resultant structure of this turbulent flame that you see is not a property only of the flame or a property only of the turbulence, it is a property that emerges due to interaction between the turbulence and the flame. So, you have to understand this, one has to know the turbulence as well as combustion very well. So, that is why we have spent in this class, in the previous classes we have spent so much time on understanding the basic properties of flames. Okay. So, you have to understand the basic properties of the flame, you have to understand both the basic properties of turbulence, and then only you can understand this kind of turbulence flame interaction. But this is what is some form of this is what is happening in a gas turbine engine, right. So, this is a very simplified version of what is or a unit version, not a simplified version, it is an unit building block of what is happening in the gas turbine is happening in the gas turbine engine. So, it is important to understand this. So, there is as you see it is a beautiful phenomena, it is a very complex phenomenon also, and that is why it makes challenging, and that is what makes this scientific study on turbulent premix flames very enriching. Okay. So, there is a continuous interaction between turbulence and the flame, and of course, as you see that the turbulence interacts with the flame at a different length scales that is captured in this video. Okay. Now, as I have said that this of course in an engine the flame can be more complex due to presence of shear etc. Here just it is a turbulent flow which is carried by a mean flow into this by a mean flow carries this turbulence onto this premix flame which impinges on this premix flame. Of course, in an engine as you see here that this main flame branch it's actually stabilized in this shear layers. Okay, in this main shear layer as you see it's stabilized in the shear layer. So, the presence of the shear also adds one more complexity to the flame structure. Okay, but nevertheless this we need to these are complex phenomena, but this complicated phenomena is what this complex interaction between turbulence and flame is what determines what will be the final heat release rate output from the engine, what will be where the flame will be stabilized, if it can be ignited, and what will be the final temperature profile at the exit of the combustor. Okay, so many things that is what determines this is emerges from this turbulence flame interaction. Okay. So, now to understand that how does turbulence interact with the flame, and we need to basically compare the characteristic length and time scales in a turbulent flow with the corresponding scales of chemical reaction and laminar flame. Okay. So, that is important, and we need to consider basically length and time scales of the turbulent flow and compare with the corresponding length and time scales with the flame, and then we find out under where turbulence will win, where the flame will win, and where both can be at a competitive can compete with each other. Okay. So, the comparison of the scales helps in assessing whether laminar flame structure can exist in turbulent flow. So, that is one very important, okay, that we have understood we have taken up the structure of the laminar flame in a great details. Now, the question is that is this when you have turbulence, is this laminar flame structure, whether this structure is reasonably well preserved and only it bends and folds, that is all. So, is it what is a turbulent flame just a bended form of a laminar flame? Under what conditions can that kind of a structure exist? Okay. Of course, you can expect that if the turbulence is extremely strong, okay, so then the inner structure of the of this laminar flame will be destroyed. So, in that case it may not exist like this. So, we need to find out under what regimes this laminar structure of this flame can be preserved, under what regimes this laminar structure of the flame will not be preserved and it will be something entirely new. So, the length and time scales of a laminar flame we can define like this. So, this is actually just a new notation, this LL is nothing but the flame thickness. So, if you remember that we discussed laminar flame structure like this, and this was the diffusion length scale, we defined that LD is equal to alpha by SL. So, here what we do is that we assume the Lewis number to be 1, okay, the Lewis number is equal to 1 and hence our alpha is equal to DI and our DI is equal to a common diffusivity like D. So, we do not assume any distinct diffusivities, we do not assume any distinct non-unity Lewis number. So, our Lewis number is unity, our diffusivities are all same. So, alpha is equal to DI and DI equal to D, this means alpha is equal to D and then we can replace alpha with D. So, our LL, which is a characteristic laminar flame thickness, okay, this is a characteristic laminar flame thickness, is essentially D by SL. So, this is what we already obtained before from the laminar premix flame class. So, if it is D by SL, the corresponding time scale is essentially LL by SL and which we can write by as D by SL square. So, that is what we have done. Okay. Now, in a turbulent flow field, the length scales and time scales, okay. So, we have got two essentially there can be other length scales also, but in you have got essentially two bordering length and time scales. One is at the beginning of the inertial range you get this integral length scale, and right at the end of the inertial range, after that in the dissipative range you have got the Kolmogorov scales. So, both the time scales and the length scales can correspond to integral and Kolmogorov integral or Kolmogorov time scales. So, we have essentially then for flames you have the length scale as LL, for turbulence you have L0 or eta, and similarly the time scales for this you have tau L, whereas for this you have tau 0 and you have tau eta. Okay. So, these are the different the length and the time scales that you have. Okay. So, these are the different length scales and time scales of it. Now, of course, we also assume that the Schmidt number, that is Schmidt number is nothing but nu by D. So, that is also equal to unity. So, essentially all our Schmidt number, Prandtl number, everything is unity, and our Lewis number is also unity. So, all these non-dimensional thermophysical properties are essentially same. So, all these non-dimensional numbers are same and all the thermophysical properties are essentially same. So, nu essentially nu is equal to T is equal to D is equal to alpha. Okay. So, and these regimes that we will define, it is important to remember that these regimes which we will define are only tentative and should not be used as to take as strict demarcations. So, it is not that these regimes that we will define is just only it exists, only this kind of structure only exists within this regime strictly and it cannot be found outside, because the regimes, this boundary is a little bit blurred. What I mean will become apparent very soon. Okay. Now, some important non-dimensional numbers are obtained on comparison of scales between turbulence and laminar flame, which help in making the regime diagram. So, what are these non-dimensional numbers? So, the first non-dimensional number, of course, you can understand in a turbulence class, of course, the important the non-dimensional number is Reynolds number. Now, since our Reynolds number, our nu is equal to D, our Reynolds number, which we essentially define as in terms of the u0 prime, which is essentially the u RMS, right. So, it is the u prime, it is the root mean square of the fluctuating component of velocity. Okay. So, that is defined as u0 prime and that is used in our definition for Reynolds number. L0 is my integral length scale. Okay. So, u0 prime is the RMS of fluctuating component of velocity, and L0 is the integral length scale. If you have any questions, you can go back to the previous notes of turbulent flows where we defined all these properties, and this is of course divided by nu. Now, since nu is equal to d and d is equal to SL times LL, we can replace nu with SL times LL and we get essentially u0 prime by L0 divided by SL times LL. Okay. So, then it becomes the Reynolds number essentially becomes a ratio of your characteristic velocity scales, turbulent velocity scale to the flame velocity scale or flame speed scale to the ratio of the turbulent length scale to the flame length scale. Okay. So, that is what it becomes. You can clearly see here that the numerator in this and this one is essentially this guy is essentially the ratio of this first term is the ratio of your okay, this is the ratio of your URMS to flame speed, and this is the ratio of L0 by LL. Okay. So, clearly this tells you about that how strong the turbulence is as it as the Reynolds number should tell. There are other numbers also, and there are other numbers like something, there is something called a Kolovitz number. What is a Kolovitz number? Kolovitz number is essentially, I will just show the derivation here clearly. Kolovitz number is the ratio of flame time scale to the Kolmogorov time scale. Okay. Now, I can write that tau L, which is a unit of second, okay, in terms of that characteristic diffusivity, which has an unit of meter square per second, and the length scale, which is a unit of meters. Okay. So, I can write this tau L as LL square by d. So, this is meter square, this is meter square per second. So, tau L is equal to seconds. Okay. Similarly, I can write tau eta as eta square by nu. Why? Because you remember, by Kolmogorov's first similarity hypothesis, the small scale should be determined only by nu, and if required by epsilon. Okay. So, of course, in the definition of eta you have a definition of epsilon. So, here we can just form this tau eta by eta and epsilon and nu. Okay. Now, we can replace this by d, okay, because nu is equal to d. So, we can write this as d. So, then this guy becomes nothing but LL square by eta square. Okay. You can just erase this. Okay. It is only becomes just simple LL square by eta square, and then I can write LL square by L0 square, which is my integral length scale, to L0 square by eta square. So, it becomes then the ratio of the square of the ratio of the flame length scale to the integral length scale and the integral length scale to the Kolmogorov length scale. Now, what is the ratio of integral length scale to the Kolmogorov length scale? Okay. That we should derive. Now, for that, if you remember, then we have to find out essentially what eta is. Okay. If you remember the definition, once again going to Kolmogorov's first similarity hypothesis, eta should be only based on nu, that is the kinematic viscosity, and turbulent kinetic energy dissipation rate. Okay. So, if eta has a length of meters and epsilon has a unit of, eta has a dimension of or units of meters, and epsilon has this turbulent kinetic energy dissipation rate has a dimension of meter square per second cube. and nu has dimension of meter square per second, then eta must be defined, we have to eliminate s. So, it is essentially defined as nu cube by epsilon to the power of 1/4, and that is the definition of Kolmogorov length scale. Okay. Fine. So, if I write eta by L0, what I get is nu cube by epsilon to the power of 1/4 by 1 by L0. Now, what is epsilon? Epsilon is nothing but u prime cube by L0. So, we can just substitute. So, then this becomes now this L0 can go inside, and this will have can go inside here, this will have cube once it, because it is inside. So, then it becomes nu cube by u0 cube times L0 cube to the power of 1/4. What is this? This is essentially Reynolds number to the power of 3. So, then this becomes RE0 to the power of 3 by 4. Okay. Now, this is a very important thing. So, this tells you how the scale separation looks like. So, eta by L0 is equal to RE0 to the power of minus 3 by 4. Okay. This is a very important expression. So, as the Reynolds number increases, the scale separation increases. So, that is why when in a turbulent jet, when the Reynolds number increases, the largest length scale remains same, but the smallest length scale, it becomes finer and finer, and the smallest length scale decreases. Okay. So, now we can then put this thing here. So, essentially my Karlovich now becomes or this is one way to write it, the other way would be okay. We have just substituted the nu by with SL times LL, that is the substitution we have done. And then this comes to be equal to this is minus because this is inverted, half times u prime by SL to the power of 3 by 2. All right. So, then this implies sorry, it cannot be seen here. So, that is what we have got here also. So, or we can just write this here. So, u prime by SL, that is a ratio of the turbulent velocity scale divided by the flame speed scale, is equal to Kolovitz number to the power of 2/3 times L0 by LL, that is the integral length scale by the flame thickness to the power of 1/3. So, we can define another non-dimensional number. Now, this is based on the integral time scale to the flame time scale. Remember, Kolovitz number is a ratio of the flame time scale to the Kolmogorov time scales. So, the turbulent Damkolov number is based on the ratio of the integral time scale to the flame time scale, okay. And we can define the integral time scale is nothing but L0, that is the integral length scale divided by the u prime RMS, that is the RMS of the fluctuating velocity, and the flame time scale is of course LL by SL. So, we can write this simple Damkolov number as L0 by LL at times u prime by SL inverse. So, you see we have got numerous non-dimensional numbers. That Reynolds number is essentially, if I just write Reynolds number here, we have written u prime by SL times L0 by LL, okay. So, you see these groups u prime by SL, that is the ratio of the turbulent RMS velocity divided by the flame speed, and the ratio of the integral length scale to the flame thickness, these two groups, these two non-dimensional groups appear repeatedly, and these are basically used to construct the different non-dimensional numbers, okay. So, then we can use these two groups u prime by SL and L0 by LL to essentially construct something like a regime diagram. So, we put L0 by LL, that is the ratio of integral length scale to flame thickness, okay. We put this on the x axis and we put the ratio of RMS of fluctuating velocity to the flame speed on y axis, okay. So, this is u prime by SL is that the ratio, and this is the other ratio. So, then we can construct this regime diagrams. Now, we will discuss the different regimes, okay. So, you see that the parameters that we had, okay. So, the parameters that we had was essentially Reynolds number was u prime by SL times L0 by LL, okay, or u prime by SL is equal to RE0 times L0 by LL to the power of -1, okay. The other parameters was Damkolov number is equal to u prime by SL is equal to Damkolov number inverse times L0 by LL. Okay. And Kolovitz number is u prime by SL is equal to k to the power of 2/3 times L0 by LL to the power of 1/3. Okay. So, this you see the important thing is that in the log plot this will be appear just like straight lines, okay, u prime by SL, and so if this is, we choose this as x and this as y. So, it is essentially x is equal to some constant times y to the power of 1/3. So, in a log plot the 1/3 will just become come come on the left hand side, come on in as appear as a coefficient, and it will appear just straight lines. Okay. So, this regime diagram is essentially on a log plot. Okay, both the axes are on log scales, one log with logarithm base 10, and all these lines, these different lines are essentially this lines is constant, Reynolds number constant, Amklo number constant, Kolovitz number. This will appear as essentially as straight lines. So, the Reynolds number equal to one line is basically what demarcates between a turbulent flame and a laminar flame. So, this is this line, that the Reynolds number is equal to one line. Okay. So, of course, you see the Reynolds number, this is x y is equal to constant, and in a log plot this rectangular hyperbola will appear as a straight line with a negative slope, okay, as you see here. And so, anything beyond this regime, okay, is a laminar flame regime. So, we are not interested in this regime. Okay. Now, if the u prime by SL is less than 1, okay. So, if the u prime by SL is less than 1, that means that flame speed is much faster than u prime, than the fluctuating velocity. So, the flame will propagate even before the fluctuating velocities can cause any disturbance of the flame will cross them. Okay. So, this will be mildly, this side of flames will only be mildly wrinkled by the will be just mildly wrinkled with the will only be just mildly wrinkled with the by the turbulence. So, this regime is essentially called the wrinkle flame regime. So, this regime, this u prime by SL is equal to 1, which is less than 1, this will be on this will be called the wrinkle flamelets regime, okay, because the flame speed is smaller than the fluctuating velocities, all right. Now comes the two interesting regimes called the corrugated regime and the three interesting regimes, essentially the corrugated regimes, the reaction sheet regime and the well starred reactor regime. Okay. Now, the corrugated regime is essentially the boundary between u prime by SL equal to 1 and the Kolovitz number, the flame Kolovitz number equal to 1 line. Okay. So, this Kolovitz number equal to 1 line, okay, will appear. So, if we put in this expression, if you put Kolovitz number equal to 1, okay, the Kolovitz number equal to 1, if you remember, the Kolovitz number was essentially the ratio of the flame time scale to the Kolmogorov time scales, all right. So, if the flame time scale is equal to the Kolmogorov time scales, then that essentially becomes Kolovitz number equal to 1, and this also boiled down to the fact that it boiled down to the fact that your flame thickness by the Kolmogorov length scale was also can be defined as a Kolovitz number. So, it is LL by eta whole square. Okay. So, when Kolovitz number is equal to 1, it means your flame time scale is equal to your Kolmogorov time scale, all right. Now, also it means that your flame length scale is equal to your Kolmogorov length scale. So, the flame time is equal to the Kolmogorov time, and your flame thickness, that is if this is a flame, so then if this is the flame thickness, so then the smallest eddies of turbulence, which are the Kolmogorov eddies, which is also of the same size. Okay. So, this is the idea. So, this regime is essentially composed of means this line essentially means this limiting condition is reached when the flame time is equal to the Kolmogorov time and the flame thickness is equal to the Kolmogorov eddies. In this regime, in this smaller than this regime, the Kolmogorov eddies are essentially much larger than the flame thickness. So, the flame actually in all these regimes that we have discussed, the flame actually remains undisturbed. The flame structure or the preheat zone remains undisturbed by turbulence. But now, in these regimes greater than the Kolovitz number equal to 1 regime, okay, once the flame time or the flame thickness becomes bigger than the Kolmogorov length scale, that means when the flame thickness is bigger than the smallest scales in turbulence, then the idea is that then the smallest scales of turbulence can enter into the preheat zone and distort the structure there. As such, it can enhance the molecular diffusion with turbulent diffusion in the preheat zone. Okay. So, this is the structure. Okay. So, in this regime, so if I just draw, so this regime is just simple wrinkle flamelets regime. This flame, in this regime, the corrugated flamelets regime, the flame can be strongly wrinkled like this, okay, but its internal structure will still be very much preserved. Even the preheat zone and the reaction zone, even it will be preserved. But in this reaction sheet regime, okay, what it means is that because the flame time is now greater than the Kolmogorov time, or the flame length scale, the flame thickness is now greater than the Kolmogorov length scale, the Kolmogorov eddies can now penetrate into the preheat zone and distort the flame structure there. So, this structure will look something like this. The actual laminar flame structure will not be perfectly preserved, and you can have eddies inside this preheat zone in this reaction sheet regime, and it can distort. Okay. But you still see that now only the flame thickness is bigger than the Kolmogorov length scale. There is one more length scale associated with the flame which we have not discussed in turbulent combustion, but we did discuss in laminar combustion, that is the reaction zone thickness. You remember the reaction zone thickness and the preheat zone thickness, they were given by a ratio of 1 by Zeldovich number. Okay. So, the reaction zone thickness is still greater than is still much smaller than the preheat zone thickness. But now if the reaction zone thickness, okay, if you replace the Kolmogorov this Karlovitz number definition now, instead of the flame time scale, instead of the flame time scales which was based on the preheat zone thickness and the flame speed, if you put the reaction zone thickness and the flame speed, then correspondingly you will get essentially the reaction zone thickness. You can define a Karlovitz number based on the reaction zone as your LR square by eta square. Okay. So, if now the LR square, that is, or the LR, that is reaction zone thickness, becomes bigger than your preheat, than your Kolmogorov length scale, then what will happen is that then the Kolmogorov eddies will even penetrate inside the reaction zone and can distort it. Okay. So, this can lead to this kind of a broken flamelet structure where this even this reaction zone has essentially broken up. Okay. So, once again I will summarize this. So, here these two are very for turbulent combustion, actually in the gas turbine combustion or SI engine combustion happens in basically in this reaction sheet limit, which means that why do we call it by the reaction sheet limit? We call it reaction sheet limit because here in this structure the eddies, the Kolmogorov eddies can distort the preheat zone thickness. But since the reaction zone thickness is still much smaller than the Kolmogorov sized eddies, the reaction zone structure remains undisturbed. Okay. And the reaction zone structure resembles to that of a laminar flame, which is not disturbed. It can be bent, but it is not, the structure is not disturbed, and as such we can still approximate it using in the reaction sheet limit. So, that is why it is called the reaction sheet zone, and whereas the previous part whereas the part which is preceding it, that is a preheat zone, that is now thoroughly disturbed with the Kolmogorov sized eddies. Alright. So, these are the different regimes that we have, and as you see that these lines are obtained essentially with the with this is the U prime by SL is equal to 1 line, and this line is very important, which is essentially the Karlovitz number equal to 1 line. And the importance of Karlovitz number was essentially found out by of course, this is named after Karlovitz, but this was found out by Williams. Okay. So, now this is of course very important that in this there is a distinction between these two regimes, but as I said that these regimes the boundaries should not be taken to be extremely like very sacrosanct as such. There can be flames which exist in the corrugated flamelets regime which can have a structure which is similar to the reaction sheet structure and vice versa, but mainly in this regime when you see the turbulence is also weakened because the Karlovitz number is essentially small, it is less than 1, it belongs to the corrugated flamelets regime, whereas in this reaction sheet limit, which is also called the thin reaction zone regime, is actually a very important regime for practical purposes. So, here basically as you have seen that because the Karlovitz number has become greater than 1, which means that your preheat zone thickness has become greater than the Kolmogorov length scale, and that means essentially now, and also your flame time scale has become bigger than the Kolmogorov time scale. So, then it means essentially that the Kolmogorov eddies can penetrate into the preheat zone and distort the structure. Actually, it can even broaden the preheat zone in certain circumstances, and it can essentially distort the structure. It adds to the diffusion processes. It now the molecular diffusion can be overtaken by turbulent diffusion, and the preheat zone structure is really affected by turbulence in this reaction sheet limit. But still, because as you know, because the reaction zone thickness is still reaction zone thickness by the preheat zone thickness for a normal laminar premix flame is essentially given by the 1 by Zeldovich number. The reaction zone thickness is still smaller than the preheat zone thickness, and if it is substantially smaller in the sense that this now there still the reaction zone thickness is smaller than the Kolmogorov eddies, Kolmogorov eddy sizes, then the Kolmogorov eddy sizes can only distort the preheat zone structure, and it cannot distort the reaction zone structure. Okay. So, that is why this is called the reaction sheet limit, and you still basically have a little bit of a distorted, you have a convoluted reaction zone, but the internal structure is not disturbed. But if you have a situation which you have in this well stirred reactor situation, that is, if you have a situation where your Kolmogorov size eddies have become essentially smaller than the reaction zone thickness. Okay. So, LR is even larger than eta. Okay. So, this region is essentially means that LR is essentially larger than eta. So, if that is the situation, that means the Karlovitz number is very large. I mean, it is when the reaction Karlovitz number is larger greater than 1. So, then what happens is that the flamelet structure is completely destroyed. So, even the reaction zone structure does not behave like that of the laminar flame, and it is a well behaves like a distributed flamelet. The flame becomes distributed into several parts, and it behaves approximates that of a well stirred reactor. Okay. So, this part is essentially called the well stirred reactor, or this this regime. There can be other regime diagrams also exist. The above is just one example.